This first part of NotesQuest looks at energy. We're going to start off by defining what energy is. We're then going to see its symbol in units and see how that relates to food packages, and you'll probably have a look at that in lessons 2. Then we'll look at the types and what transfers go on, 2 equations, the law of conservation of energy and how that relates to Sankey diagrams, and what is work. To start off, a definition, and that actually relates to this idea of work. To define energy, we first of all need to give it a symbol. In physics, we don't often like to write things out in full, so we can give it the symbol E, which makes sense for energy, or we can also give it the symbol W, which looks a bit confusing, but we'll see from the definition of energy why that comes in. Now, the definition that you need to learn is it's the ability of something, an object, to do work. Now, that seems a bit confusing because work is kind of what you're doing now. And no, that's not what we mean by energy, because work in physics has a different idea. If something's able to do work, it means it's able to transfer energy. Now, this is difficult to define energy because it's such a weird concept. It's something the universe just has and has always had. As to what it actually is, well, you can't just touch it, you can't feel it. So when we transfer energy, we either give that object the ability to heat up or to do work. That might be move something a distance or do something related to that. So if you just learn this definition at this level, that will help. We also need to know its units. Now, the units are what we measure it in. Just like you measure your weight, or your mass in kilograms, and just like you measure your height in meters or centimeters or feet, the units of energy, and this is accepted by all physicists, is the joule. Okay, so that is the unit of energy. Now, we don't like to write the word joule out always, so we can just shorten it to J. So, for example, an object might have 10 joules of energy, and we could write it like that. The energy of the object is equal to 10 joules. Sometimes we have very large quantities of energy or very small, and we can use prefixes before the unit. So remember, the unit was the joule, a prefix comes before it. So for example, if we have 1,000 joules, we can just say we have 1 kilojoule. The K here means kilo. So 1 kilojoule is equal to 1,000 joules. Very similar to 1 kilometre being equal to 1,000 metres. Other ones you need to know at this level is 1 megajoule, and this is even bigger, just like a megabyte, and it's 1,000,000 joules, or 1,000 kilojoules. You can see where it comes in, it's multiples of 1,000 each time. You know what other one you need to know is a millijoule, just like a millimetre. Okay, so this one here is milli, and remember the capital M is mega, so you've got to be very careful to look for capital M or little m. A millijoule is actually you divide by 1,000 before you use it. So 1 divided by 1,000 is 0.001. So it's a very small amount of energy. Let's now relate this to a package of food. And this is for a Tim Tam. And you can see this is the back of a package. And if you've got one in front of you, have a look and you'll see this here. Now let's have a look first of all at what we're interested in, which is energy. And you can see here the quantity per serving is written here. And now we can understand what these things mean. Let's write it out in full here. We have 872 kJ. Remember the K means kilo, which means it's times 1,000. So we actually have 872,000, and the J is the unit of energy joules. So we can say the energy of 1 serving of a Tim Tam is that amount. So you can see it's actually quite a lot, and that's quite normal. If you had 100 grams, tasty, you can see that we get a lot more energy. Another unit you might see on packets is calories, and you can have a look on Google to see how much calories in a joule. And that's just another unit of energy, but the one we use in physics, the one you expect to know, is the joule. Now this energy in a food is actually called chemical energy, because it's a type of energy that's stored in the atoms in the food, and your body then uses that energy to move and so on. And therefore we need to think about the different types of energy we have, because it's sometimes useful to know what one object has and what it's going to turn it into. So chemical energy is one that's stored in, for example, food. It's also stored in things like fuel, like petrol, coal, wood, anything like that has chemical energy in. And we're going to look now at the types of energy that you need to know. So the types you need to know are all listed here. We've got, first of all, magnetic. We've also got kinetic, Now kinetic is a movement, so anything moving has this type of energy. If you're still, you don't have any. Then we have heat and thermal energy. And then we have light energy, gravitational potential energy, which is energy you get as you go higher up, and the Earth's gravity is pulling you down. So if I stand on the table now that's in front of me, I'm going to gain some gravitational potential energy. Proof being that if I step off the table, I'll fall back to the ground. So it's kind of stored because of my position. Chemical we talked about, this is stored in food, fuel, petrol, and so on. Sound, you can hear that now. It's caused by vibrations. Electrical, that's in wires. So if you ever see a wire, it's nearly always electrical. Elastic strain energy, sometimes it's called. Pull back an elastic band, it's kind of stored because the deformation of the atoms there. And nuclear, which comes from atoms. Now you might be thinking, how can I remember this well? If you look, start of each of these, which is shown here, if you learn that as most kids, so most kids, MK, hate learning GCSE energy names. And remember, GCSE is the exam you may choose to do in year 11. So most kids hate learning GCSE energy names, and that gives you the start of each one, or come up with your own. Now, energy doesn't always just stay as one type, it can change between these types. Let's think of some examples. First of all, let's start with a light bulb. Now, a light bulb takes in electrical energy from the wire, and that produces light energy, and that's its main job. But if you put your hand near it, you'll know that it also produces some heat or thermal energy, and some may also produce sound as well. So this just shows you the transfers going on. The arrow represents the change in that energy type. And energy can change types. Another one might be a fan. If it's a hot summer's day, again, that's going to be electrical energy being converted, in this case, to wind, which is movement, which is kinetic energy. But there's also going to be some heat and some sound. So often we can get multiple energy types. Sometimes there'll be multiple changes. Let's say I'm on the table here holding a ball, and I'm about to let go of that ball, which is going to fall down to the ground. So at the top, because I've raised it up, it has gravitational potential energy. In the exam, make sure you write it out in full. As it falls, that's going to become kinetic energy because it's moving. There might also be a bit of sound as well, so you can write that there because sometimes you hear it whooshing through the air. But then that can also change as it hits the ground. That's going to change into sound plus heat. And then it would bounce back up and it would get some more gravitational potential energy as we go. But it wouldn't get to the same height because some energy is lost on the way to heat and sound, which we can't get back. So this shows you that sometimes there can be multiple steps in the transfer. Now there's two equations that you need to know, and I'm going to put a star next to them up here. You need to know an equation for gravitational potential energy and kinetic energy. An equation is just something that will tell you the actual amount of energy that you have. So let's start off with kinetic energy. I'm going to call it Ke. And to work out the kinetic energy, the energy, remember that's a symbol for energy, is equal to 1/2 times the mass times the velocity squared. Remember, maths squared means you times it by itself. For example, 2 squared is just 2 times 2. Because we're a bit lazy in physics, sometimes we like to write it using symbols. The symbol for mass is m, and the symbol for velocity is v. So we get this equation 1/2 mv squared. For example, if I was to run, I'm 100 kilograms, let's say, and I run at 10 meters per second, then we can work out how much energy I have. It would just be 1/2 times my mass, 100, times by the speed squared. And I can put that into a calculator. And that gives 5,000 joules of kinetic energy. If I stopped, I'd have 0 joules because my speed, which is my velocity, so think of speed and velocity as the same thing for year 9, is 0. For gravitational potential energy, there's an equation that you need to know. In this case, the energy is equal to the mass times by g, which is a constant on Earth, and on Earth it is just 10, and times by your height. So obviously the higher you are, the more energy you have. So if you know your mass, times it by the strength of gravity, and then times by the height, you'll know the energy. Remember, the units of energy are joules. So energy's units are joules. So whatever numbers you put in, you'll get an amount of joules that you have, which can be very useful to know. This image here you see is called a Sankey diagram, named after someone who kind of started using them, Sankey. So it's called a Sankey diagram. Weird name, but you'll be surprised how you remember that. And this just shows you a change of energy of an object. So you start over this side, and this shows you that we had 100 joules of electrical energy. This is probably going to be a lamp here, or a light bulb. How do I know that? Well, if you look at what comes out, we see we get light energy, which is 10 joules, and then 90 joules of heat energy. When the arrow goes straight on, this represents the useful energy, because for a light bulb, we want light. Heat is not the job of a light bulb, so you can see the arrow curls to the side, and that's because this is wasted or not useful energy. If it was a heater, then that would be useful, and the arrow would go straight on, and we wouldn't want light in that case. Why are these useful? Well, the width represents how much energy we have, and you can see that we start with 100 joules, and at the end, we finish with 10 joules of light and 90 joules of heat, which you'll notice adds up to 100. And this is an important concept in physics. It's called the conservation of energy. This idea is really important because it tells you that energy cannot be created or destroyed. So it cannot be created or destroyed. That means we can't just produce energy out of nothing, and we can't just destroy energy. So I couldn't start with 100 joules and end up with 0. It can only be transferred. Or it can only be changed from one type, e.g. kinetic, to another, e.g. gravitational. And this is a really important idea. So actually, funny enough, the universe started with an amount of energy when it was formed, and we're never going to get more or less. It's just going to change types between those types you learnt earlier. And this is very nicely shown in a Sankey diagram because you can see what you start with, and that's always going to be equal to what you end up with. Energy cannot be lost. We couldn't have, say, 9 joules here, because that means 1 joule would be lost somewhere in this diagram, which just can't happen. So if we go now back to our original diagram, which showed us this unit, you can see that we've now talked about what energy is, the symbol in the units, which was the joule. We looked at a food package, looked at types and transfers and 2 equations, one for GPE and one for kinetic energy. And we talked about conservation of energy. So the last thing is work. Now work done can be calculated by basically timesing the force you apply to an object, how much push or pull you do, and how far that object moves. So you can see when something has energy, it has the ability to do work, as we said, which means it can make something move a distance, as we can see from this equation. Now, work done can be thought as the same as energy at GCSE and Year 9, and the units are joules, okay, because it is basically the same as energy. So where does this come into this topic? Well, let's say I lift up Mr. Garner's favourite physics book onto a table. It was on the floor. Well, I'm doing work against gravity because I'm applying a force and I'm moving at distance, let's say 1 metre onto the table. So I can work out how much gravitational potential energy that book now has by timesing the mass of the book times by gravity times by height. And that's going to be equal to the amount of work done by me. Because I'm doing work, I'm applying a force and moving this distance, I'm using up some of my chemical energy from my breakfast to move it onto the table. And to work out how much I've done, I can use this equation. And you'll do something similar in class where you run up some stairs and you work out how much energy you use to get up those stairs. So that's really all you need to know for work done in Year 9. We'll look at force in a later topic, and it has units of newtons, which we'll see later on. The final thing we need to look at is the energy transfers during freefall. So here's Mr. Gardner in his plane, my plane, optimistic, and I'm going for a little jump out. Now, first time, I'm going to do it, imagine that there's no air here. So somehow I'm on a weird planet where there's no atmosphere, and I jump out. Up here, I have lots of gravitational potential energy, because I'm high up. Remember, that's a stored energy I have because the plane's taken me up. It's done work against gravity. It's now stored because of my position. But when I jump out, I'm going to lose some GPE, and I'm going to speed up and gain kinetic energy. As we fall, I gain kinetic energy and lose gravitational potential energy. So if I draw that as a diagram, So in simple forms, in this case, it's nice and easy. My GPE is just transferred into kinetic energy because there's nothing else there. But let's say I now do this on Earth. Out my plane I come. Whee! Look at all this fun I'm having. Fun. Down we go. This time there's air, which is good because that's going to cause resistance against me. So again, up here, I have gravitational potential energy, GPE for short. As I fall, we know I'm going to speed up. Initially, I was stationary relative to that plane, so I had no kinetic energy. And it's all going to become kinetic energy as I speed up. We know that I speed up. But that's not all that happens, because some of that energy is going to become heat energy. You might be thinking, well, where's this heat coming from? Well, as I fall, there's millions and millions of little air molecules there, and I hit those. And as I hit those, it's kind of like friction. It's like me rubbing my hands together now. It gets hot. So it kind of actually heats up the air and the surface of your clothes. If you've seen any of those Apollo films, or you've seen a rocket coming, or an asteroid coming into Earth, if we have Earth here, we've got the atmosphere around it. And you know, as a rock or asteroid comes in, it burns up. That's because it's rubbing against the air molecules and heating up. It's rubbing against those millions of air molecules because it's coming up very fast, heats it up. So when we have air, some of that gravitational potential energy is transferred to heat, and most of it also becomes kinetic because I speed up, and hopefully I have a parachute to deploy. With no air, there's nothing to rub against, so all of it becomes kinetic energy. So I'll just keep going faster and faster. To help you fill in the table in the NotesQuest, you can pause the video and use this here. Other things to think about as well are the units for different things. Remember, you can just Google those units. So, for example, one of them asks for distance. So you could just Google distance, GCSE physics units. And I'll help you out with that one. You should get the idea that it is measured in meters with the symbol M. So remember, in physics, there's always an amount of something, a quantity, say in this case distance, and we have a symbol for that. In this case, it would be little d. It also always has a unit. In this case, it's the meter, and that's measured in M. So there's always a quantity, so distance, force, energy, and a symbol for that, and a unit and a symbol for that. Hope you found this video useful. Thank you for watching.